You build an autonomous agent. In a static testing environment, the logic holds up, but the moment you deploy that agent into the live, dynamic conditions of production, the system breaks down. These breakdowns manifest as three specific structural system failures: oscillation, overload, or freezing. Typical engineering attempts to solve these as isolated logic bugs. We open the system prompt and add natural language instructions, telling the model to think carefully or stop repeating itself, attempting to patch a structural deficit with better phrasing. These production failures are deterministic system dynamics failures. Resolving them requires mapping environmental variables to the LLM's API parameters using the RPCS-1 Cognitive Systems Framework. Stabilizing production agents requires a transition from trial-and-error prompt engineering to a rigorous mathematical calibration of receiver parameters. The RPCS-1 framework translates abstract environmental conditions into exact parameter values across 5 cognitive receiver primitives. The first is temporal integration, or TI, controlling context window strategy and maximum token limits. Signal gain, or SG, dictates how strongly the agent amplifies data, mapping inversely to temperature. Filtering threshold, or FT, determines how conservatively the model gates actions, driving tool use strategy. Update elasticity, or UE, measures readiness to revise internal assumptions, setting the foundation for retries. Finally, ambiguity resolution, or AR, defines commitment aggression in highly uncertain environments. Once these 5 primitives are configured, they form a deterministic control layer that dictates agent behavior, effectively overriding raw reasoning errors. The first failure mode, oscillation, is characterized by an agent refusing to commit and looping through identical tool calls without executing a final action. This occurs when high signal gain and high temporal integration are deployed into a fast-changing environment. This can be diagnosed using the core axiom of the RPCS-1 framework, the matching principle. It states that optimal temporal integration, TI, must be inversely proportional to the environment's entropy, or rate of change, H. In highly dynamic environments, new variables constantly overwrite old ones. Maintaining a large context window forces the agent to reconcile incoming signals with conflicting, outdated data, causing execution gridlock. To fix an oscillating agent, we drastically shorten the context window to match the high entropy and lower the signal gain. Disregarding the entropy rate of the deployment environment leads directly to oscillating behavior, regardless of the underlying LLM scale or training. The overload failure mode occurs when an agent bypasses its standard execution paths and generates hallucinated tool calls. This happens when an agent attempts to act before gathering sufficient system state information. The diagnostic indicator is a high signal gain over-amplifying incomplete signals, paired with a critically low filtering threshold. Raising the filtering threshold enforces stricter tool gating, while lowering signal gain prevents overreaction. Supporting this lowered signal amplification requires extending the integration period and implementing a distinct retry strategy to allow the agent to fully map the system state. Hallucinated tool calls in production are generally a result of premature action gating driven by misaligned receiver parameters. The final structural failure is the freeze. The agent produces endless hedging language and thinking tokens, but never triggers a tool. The agent possesses the necessary data, but it is permanently trapped behind its own conservative action filters. This is an interaction between extremely low update elasticity and a maximum filtering threshold. The agent becomes stuck in a feedback loop, attempting to validate an internal model that the high filter refuses to pass. To unclog the system, we lower the action gate and increase update elasticity. This allows the agent to discard its stalled internal model and rotate its approach until an execution path clears the gate. We then adjust the ambiguity resolution parameter. This forces a commitment protocol in environments where high-confidence data is unavailable. Optimal performance requires a precise balance between action gates and the environment's inherent ambiguity. This theoretical framework is deployed utilizing the RPCS-1 Agent Tuner SDK. The configuration requires deterministic inputs, the environment entropy, stake levels, and the specific commitment style of the task. The system returns exact outputs. For a customer support agent in a dynamic environment, it recommends a temperature of 0.52 and a TI cap of 30. The RPCS-1 framework provides a traceable, mathematical mapping of environment dynamics directly to API parameters. When an autonomous agent breaks in production, align the model's integration window to the environment's entropy to stabilize the system.